Thank you very much. Thanks for the introduction. So yeah, thanks very much for the invitation to speak as well. This is, I think, the first person-facing conference that I've spoken at for three years. So it's been quite a bizarre experience for the last 3 years, speaking to lots of virtual audiences around the world without even knowing who's present, if anyone. So I appreciate the fact that there is actually a physical audience left at this time of day, just between us and the cocktails. So the invitation gave me the opportunity of coming to this quiet backwater called Melbourne, travelling from my futuristic metropolis where I live normally, which is Canberra, where we have really advanced technologies, including mobile phones, food delivery services, although I've seen a few of those in Melbourne, and actually something quite interesting, which is a drone delivery service that's been trialled in Canberra by one of the Google companies, Wing, over the last years. So my house is right under the flight path for a lot of these drones that go buzzing overhead. Luckily not at night time, just during the daytime, and they deliver all these exciting goodies to my neighbours. Unfortunately, not to me. Evidently, we have trees and power lines around our house. So instead, I actually came up with an idea of building my own virtual, unfortunately, drone delivery service, and that is the origin of this talk. Who am I? Paul Brebner. My background's R&D in distributed systems and performance engineering. For the last 5 years, I've been the open source technology evangelist for Instaclustr, which is now Instaclustr by NetApp. I've written lots and lots of blogs about open source technologies, built a few demo applications, and occasionally given talks, such as this one. Some of the open source technologies that I've talked about include Cassandra, Spark, Kafka, OpenSearch, Redis, and now Uber's Cadence. Instaclustr provides a managed platform using open source technologies. We've got technologies for storage, streaming, analysis, search, and now orchestration. So the latest edition is for workflow orchestration with Cadence. So workflow orchestration is pretty simple. It's basically the idea of having tasks and being able to perform them in order, in sequence. So you might start, you have a task, you have another task, and then you finish. It's quite straightforward. And you can do this with cadence. So pedaling with high cadence is called spinning in the bicycle world. Mashing or grinding is slow and bad. So you want cadence, which is a good name, I think. Cadence is fault tolerant. Workflows can and will fail. Cadence is fault tolerant, and workflows continue from the point of failure. Cadence is horizontally scalable. The number of workflows is, well, at least theoretically, unlimited. Cadence workflows are just code as well. So here's an example of a workflow implementation with two tasks executed sequentially. As you can see, it's pretty straightforward. You just basically call the two tasks with some input and output arguments. There's some boilerplate code that you need as well. It's not quite as simple as this, but in essence, this is all you need. Cadence Architecture. So our managed service for Cadence has a number of different components. At the back end, there's a couple of different database options for persistence, and also Kafka is used and OpenSearch for what's called advanced visibility, so you can actually check the state of your workflows and find them and things. The Cadence servers is where all the tricky stuff goes on, and there's a whole bunch of APIs which allow customer-managed clients and workers to connect to that system and do interesting things. So there's a whole bunch of Cadence client APIs, the activity, the client, the workflow, and the worker API. I won't go into too much detail, except there's quite a rich set of APIs, which I thought was the relevance for this conference in particular. So how does Cadence fault tolerance work? Well, thankfully, the previous talk actually talked about some of this as well, which is great. So I love Kafka and I love event sourcing, and Cadence actually combines both of those things. So essentially, we have history and replaying of events. So as the workflow is executed, you start the workflow, you execute the first task, you end the first task, and you're at a particular point in the workflow. And as that happens, the workflow history is being written to a database. So if something goes wrong, your workflow fails, the workflow state is recovered by replaying the history. And the failure causes the complete history to be replayed. The replay recreates the workflow state and also where you are up to in the workflow, which is quite important as well. You need to know where to resume your execution of the workflow. Cadence Activities. Okay, activities, including perhaps backward cycling, can fail. Cadence Activities are core to Cadence. Remote calls in particular can fail, so you wrap them in activities. They can contain any code you like. Activities are executed at most once and can be automatically retried on failure. There's a couple of restrictions around workflows, around activities in particular. Replaying must not produce new history events. Activities are executed at most once. This ensures that once they succeed, then the result is essentially immutable or fixed. And there's an example with a slightly more complicated workflow where the two activities are executed at most once. And there's also restrictions for the actual workflow itself. So again, replaying must not produce new history events. I've said that before, but that's the same at the workflow level as well. Due to replaying, workflow code is executed multiple times, so it must be deterministic. You can use built-in methods for things like time, sleeping random, and side effects to make sure that they are not replayed, that you only get the one result, and that's reused again. So what are some good use cases for Cadence? Well, hundreds to millions of running workflows, long-running processes with some sleeping and scheduled tasks happening perhaps long periods apart, stateful fault-tolerant applications, complex workflows, integration with unreliable external systems, integration with streaming and event-based systems, for example, Kafka, and examples, oops, I've got something strange happening here. The aliens are trying to contact me. For some reason, go away. And examples where there are short workflows with hundreds of steps rather than, say, long ones where there's thousands of steps involved, which may take longer to replay the history upon failure. So some good examples are typically found in the financial, retail, and delivery sectors. So that was my example that I came up with, spinning your drones, a drone delivery application. So there's some very simple drone workflow steps. Basically, the drones start out, they're charged, ready to go at some base. They get an order to deliver. They fly to the order location and collect the order. Then they fly to the delivery location and drop the order, and then fly back to base, recharge, and repeat. And the process just goes around and around, basically. So here's an example of a drone delivery flight. I've used a sort of a desert island example as the location, with the drone base in some sort of volcano, perhaps a secret lair. The drone master keeps all his drones there. Basically, the drone flies from the base to the order location, which is a little village perhaps there. It picks up the order and delivers it to perhaps the pirates who are on a boat off the coast. And then once the delivery has occurred, it flies back and goes back to the drone base again. So in order to do that, you actually have to do lots of waypoint flight calculations. So here's one of the legs as an example, the returning to base example. The drone flight path is computed in an activity, uses location, distance, bearing, speed, and charge remaining, and this is done every 10 seconds to make sure that the drone doesn't get too far off track every 10 seconds. If the activity fails, the drone won't crash and will continue flying from the last location because it's using activities. So I've got a couple of diagrams just to show what's going on at the system level. So this shows part of the system. It's a swim lane diagram showing the first workflow, which is the drone workflow. Basically, the drone moves from the start to the ready state, waiting for an order, performs movement activities, recharges, and repeats. Now, it's interesting, orders are also stateful in my system, so they are actually implemented as a workflow as well. So we actually have two Cadence workflows for this example. So the second workflow is the order workflow. That also starts, it generates the locations, gets ready for the drone to come and get it, it updates the locations, and then ends once a delivery is successful. You also, therefore, need coordination between workflows because you've got two of them. So you can use asynchronous signaling between workflows. Yeah, I'll go into that in more detail in a second. So the next part of the story really is around Cadence integrating with Kafka. So Kafka, for those who don't know, and obviously after the last talk everyone knows what Kafka is, so this is a bit redundant, but it's a distributed pub-sub streams processing system. It allows distributed producers to send messages to distributed consumers via a Kafka cluster. And it uses topics to loosely couple producers and consumers. Well, that's Kafka at a very high level. So integration of our system with Kafka adds, for a start, a Kafka cluster with 3 Kafka topics, which are the top 3 new swim lanes in that diagram. There's 3 new Kafka producers and 2 consumers. And it also involves starting a workflow from Kafka as well. And also using a Kafka microservice to coordinate the drone and order workflows. So really we're doing Cadence orchestration plus Kafka choreography, which is sort of maybe a drone ballet type of orchestration or integration coordination pattern. So just in a bit more detail, just to see what goes on for an actual example. Step 1, customer places an order, presumably using some sort of mobile phone app or something like that. The order is sent to the Kafka new orders topic. Step 2, the start new order workflow occurs. The Kafka consumer gets the order, starts the new order workflow using the Cadence client. Step 3, the order is ready for drone pickup. There's an activity involved in this. It sends the order ready message to the orders ready topic. Step 4 is the start of the drone workflow. As an activity, it sends a drone ready message to the drone ready topic. The Kafka consumer gets an order ID and sends the signal back to the drone to start the order pickup. Step 5 in the drone workflow is where the drone is flying to collect the order. So that's an activity, fly to the order location. That's where it's doing all the computation for the leg motion calculation. And eventually, at the end of that activity, it reaches the location and collects the order. Step 6, also in the drone workflow, it flies to the delivery location this time. And that's also done in a separate activity, fly to delivery location. At the end of that, again, once it reaches where it's delivering the order, it drops the order. But during that, the motion of the flying from the order location to the delivery location, it's actually sending constant location updates and state updates as well to the order workflow every 10 seconds. At the end of that, it flies back to base again and recharges and gets ready to start a new delivery when it needs to. Yep, all right, I don't know how to get rid of that, but kill it, there we go. So the step 8 of the order workflow involves a constant updating of location. So it receives state and location signal from the drone workflow, updates its internal state, and finally when it's delivered, then it ends the workflow. So that was probably a bit hard to take all into account in one sort of go. So I've got sort of a little animation here which just shows you the state. The green dot represents the sort of the order state, and the orange dot represents the drone state. And I'll just skip through it just so you can see what's going on in terms of the events and state change. And that's it, I think, the end. And it's recharging back at the base again. So you can see there's a fair amount going on there, coordination between the different workflows and with the Kafka system as well to coordinate things that are going on. So I said that one of the features of Cadence is its scalability. So I was interested to see how many drones we could actually get flying, virtual drones. Of course, one of my workmates was worried I was actually setting up a drone delivery service, and he was saying, have you got the right licenses and stuff? What about the neighbours and birds? And anyway, yes, no, it's only virtual. So here's an example of the clusters that we used for getting these results. So it's all running on AWS. The Cassandra database is the cluster that's got the most resources of 18 cores. Cadence has 6 cores and the client system has 8 cores. And so the first test I did was really sort of a flat-out load test just to make sure that I could get sensible results. So this is running faster than real time, so the drones are essentially only taking a few seconds to actually do the whole delivery circuit each time. But that enabled me to stress test the system, and we reached a peak of about 50 concurrent drones that were able to be flown with those resources. For a more real-time system where we actually allowed it to fly at a simulated 100 kilometres an hour with random pickup and delivery locations and things, we managed to get 2,000 drones flying concurrently, which is actually 4,000 workflows because, as I've mentioned, there's an equal number of order workflows as there are drone workflows. So that actually gives 4,000 workflows, which divided by the number of cores in the system gives about 125 concurrent workflows that you can run per core of the system available. So if you're interested in any more information about this type of architecture and Cadence in particular, we're actually working with the Uber people that are the open source people providing Cadence at cadenceworkflow.io. So we are providing some of the use cases for documentation, and here's one called the Mega Burgers polling example. It illustrates integration of Cadence with external third-party REST APIs for order state updates using polling. There's the URL for my blogs. There's quite a lot there on lots of open source technologies. This talk is based on a series of about 6 blogs on Cadence, and you can try us out if you're interested as well. So there's a 2-week free trial period for any of these managed services, but Cadence in particular. And finally, here's a visualization of my drone delivery service running from my backyard in Canberra. Just 20 drones flying at once. They all start at that location, and then they deliver. They go to the orange locations to pick up an order, and then once they've done that, they then fly to the red locations to do the delivery, which then change to green when the delivery is successful, and then they fly back to my backyard again, and so on. And I'll let that run if there's any questions at this point as well.
Okay, thanks, Paul.
Thank you.
Amazing.
Thank you.
How would you use this sort of service to proactively detect bottlenecks and look at resource or capacity planning? So, example, this morning I arrived at Melbourne Airport. Uber's got the whole lineup of taxis,
Yes.
and there's 50 people waiting and no taxis. Right? Like that's an incredible use case.
Yep.
And
Yep.
failure, and it's relevant because it's
Interesting. Well, I mean, in terms of using it for something to solve a logistics problem, I guess that's precisely what I was doing here. And in fact, there was a bottleneck in one of my implementations around how you matched the drones to the orders. In fact, that has to be done quite carefully, and the way that I have explained it today is the correct way. There was an incorrect way that I previously used, which meant that there was actually a bottleneck in my system, which caused a bottleneck in the real system as well. Some of the orders were getting queued up and the drones weren't coming to get them fast enough. So there's a bit of tuning and architectural design work required to get Cadence and Kafka to work together at high scalability. And I guess, I mean, if you're trying to actually solve real-world problems with the resource bottlenecks and things, you could add some predictive analytics in there to try and make predictions about when resources might need to be available and things.
The thing is, like, as these systems become more black box and complex, it becomes harder to trace the in-system and code where possibly to detect the problem, right? And the explainability becomes lower.
Yep.
So, it's wonderful that we're solving these problems, and I'm like, as an engineer, I'm like, damn, I wish that would take me a year to write this code. So.
Well, yeah, I mean, they've done all the hard work. It is relatively easy just to write workflows without having to worry about all the extra code required for the persistence and scalability of the system. I didn't talk about visibility into Cadence workflows, but there is quite a sophisticated GUI, so you can actually trace workflows as they execute and see where they are up to. and detect problems and manually, if necessary, even try and fix them and things too. Yep. I don't know how to do the order. Maybe we'll go clockwise around.
Yeah. So what is your process like to select Cadence as your tool of choice? You have a lot of other open source tool systems these days as well.
Yep. Yeah, that's absolutely true. Yes. I get mainly scalability. That's because it's using this event sourcing approach that is fairly unique as far as I'm aware of, and it really means that it will handle the throughput for very large enterprises like Uber Eats is built on this technology. If you don't need that level of scalability, it's still potentially useful though, because it means you can still write quite robust failure-proof workflows with not much effort, basically. Yeah. Yes.
When integrating with Kafka, did you have any problems with achieving once and only once delivery, so that you didn't ever dispatch two drones in the same order, or have an order somehow fall through without having a drone dispatch?
No, to be honest, no, there weren't really any problems around that with Kafka. I mean, the way I had it configured was pretty idiot-proof, and me being an idiot, I would have encountered that problem if it had occurred, but I didn't, so this time around. I have encountered that problem before, particularly in mirrored Kafka systems. It's quite difficult if you've got two geographically distinct Kafka clusters that are replicated using mirroring. That is a slightly harder kettle of fish to ensure exactly once delivery across those systems.
Would there be a way to do deduplication if two messages were delivered in the workload layer?
Yeah, yeah, it's an interesting question. I guess in theory the drone will only get one order. That's the way I've designed it. So we'll just take off and head to the one order that it's been allocated. I had thought about it being able to have multiple orders, perhaps to try and optimize the system or something, but I haven't thought about that extension yet. But now that you've mentioned it, maybe I should think about that. Oh, yes?
Where's the, so is it all in memory? Like, where's the fault tolerance on the...
Yeah, it runs in memory. It doesn't have to. And if you tell it not to run in memory, then it will just do the replaying every time, basically. For every state update, it will just run the whole history again and work out where it's up to. So you can force it to do that. Say for long-running workflows, you may not want them in memory. If there's only one activity, like a day or something, there's probably no point having the workflow in memory at all. But if you've got a system like mine where it's just running flat out, you really need to run it in memory as well.
It's more to try and figure out maybe there's a combination between what James was talking about, which is basically writing back to the Kafka queue at a point that basically allows you to maintain state in real time. So you can always recover if on failure.
It's got the concept of workers, so it actually has sort of re-implemented part of Kafka as part of Cadence. So the workers are essentially asynchronous pool-based components that are just sitting there, essentially getting workflow events from a queue internally in Cadence. So it's sort of got a Kafka architecture internally anyway, which makes it pretty idiot-proof. So, yeah. Looks like my deliveries have finished. And so have we, I think. So thank you very much for coming to the last talk of the day. So, yeah. Right, if anyone's got any questions, just maybe ping me on LinkedIn or something. Yep.